Okay, so there, the resin or the mixture of monomers would be heated and it would form a molecular network through a chemical reaction or polymerization reaction. And this would set the final form of the material, and there would be no option to heat the material and reprocess it, because the covalent bonds formed in that network fashion in all three directions are permanent. And once you heat the material, those covalent bonds cannot reform. The bonding circumstance is not reversible, and the material would have to degrade if any sort of flow or shape change was to happen, and bonding would not restore. So there is no melting, there is no softening of the material. It would simply chemically degrade into byproducts, and the end object would not be the same as the one that was attempted for recycling. Some thermoset examples to contrast the polyethylene, the polypropylene, the polystyrene, the polyvinyl chloride we saw, the nylon 6,6 that we saw. Some thermosets are urethane, epoxy, and of course the bakelite material that we've seen, or phenol formaldehyde. Polymer. And these materials, once heated, form that molecular network, and that is the final form of the material. Okay, so here's a table that we've seen before for some common repeat units. So here we can see the repeat unit for polyethylene. We can visualize that the polymer chain extends linearly in its covalent bonding. There would be some potential for secondary bonds between these chains. But because there is no linking between chains, that is primary based, no covalent bonds between chains, we can say that this material is thermoset or thermoplastic. Take a moment to guess. Pause the video if needed. Hopefully you were thinking this was a thermoplastic. Okay. Polyvinyl chloride mentioned a moment ago. So again, the bonding goes in a linear fashion here in its primary bonding. There is no primary bonding to the neighboring chain. And so again, this would be a thermoplastic polymer. Likewise, for the cousin material here, that is polytetrafluoroethylene, where all side chains are not hydrogen or chlorine, but in this case, fluorine atoms. And that would also be a thermoplastic because we do not have primary bonding covalent bonds to the neighboring chains. Polypropylene, likewise, thermoplastic. Polystyrene, the material used in styrofoam, perhaps you know that can be reprocessed and make new materials out of that. And so that is also a thermoplastic. Polymethyl methacrylate, the polymer used in plexiglass or plastic windows. Again, only a linear covalent repeating pattern occurs here with no covalent bonding to the neighboring chain. So again, a thermoplastic. Down below, the phenol formaldehyde or bakelite polymer that we've seen. Well, this material bridges at every phenol site to potentially two other sites. So hopefully with the model that I'm sketching for you where polymerization is extended, you can see that we get extensive primary bonds where each phenol residue brings three polymer directions together. And so the functionality of the phenol is allowing for extensive network formation. So this is a network polymer. So the bakelite, as an example here, is a thermoplastic or set. Take a minute to take your guess. Of course, it is a thermoset. Okay, we've seen some of these again, so take a moment to see if you can guess what these ones are. The nylon 6,6, the polyester, and here polycarbonate. Are these thermosets or thermoplastics? So you might sketch down some answers here quickly, focusing on where the repeat bonding primary bonds would take us, and if there would be any indications in these repeat unit structures if there's bonding between chains. If you cannot settle on any bonding between chains, then there isn't, so then we would call these thermoplastics. Very good.